suppose G is a finite group and that H is a proper subgroup of G. Then the union of conjugacy classes of H is a proper subset of G. To show this, first let the size of G be n and let the size of H be m. Say there are k many conjugates of H has the union over I equals 1 to k is equal to n, meaning the union gets you all of G. So n is then less than or equal to k times the size of H, which is equal to k times m. K is equal to the index of the normalizer of H in G, which is equal to size of G divided by the size of the normalizer. So n is less than or equal to k times m, which is equal to size of G divided by size of the normalizer. Times m. Which is equal to n times m over the size of the normalizer. So we have n is less than or equal to n times m over the size of the normalizer. So the size of the normalizer is less than or equal to m, but by default H belongs to its normalizer. This is always the case. So the cardinality of H, which is equal to m, is less than or equal to the cardinality of the normalizer. Thus, cardinality of H, which is equal to m, is equal to cardinality of the normalizer. then since these are finite groups, H is equal to the normalizer of H in G. So the index of the normalizer is equal to the index of G, of H in G. Hence, K times M, which was greater than N, is equal to the index of H in G times M, which is equal to the size of G over the size of H times M. But again, M was the size of H. So we get that N is less than or equal to K times M, which is equal to the size of G, which was N. By this sandwiching, N is equal to K times M. But then, since K is the number of conjugates of H, and M is the full size of H, we must have that each conjugacy, or each conjugate by H, does not overlap. In the case that K is not equal to 1. So if K equals does not equal 1, we must have that each conjugate of H is disjoint from all others. That is, they are pairwise disjoint. But then each conjugate must contain E. Which is a contradiction, since they are pairwise disjoint. Thus, K must equal 1, which implies N equals K times M is equal to 1 times M, which is equal to M, i.e. the cardinality of G is equal to the cardinality of H. As these are finite groups, that means G is equal to H, which contradicts our assumption that H is proper in G. So we are done.